Alright, we are doing solutions to Modern Physics 1. So, the formulas that we're going to use for this part is that E energy is equal to Planck's constant times the frequency, or energy is equal to Planck's constant times the speed of light over the wavelength. And the reason we can use that is because frequency is equal to the speed of light over wavelength. Now all of this works for light, and what we have to be careful of as we do this is that we are using the correct H. One of these gives me joules, one of these gives me electron volts. And the differences there are what we want our things in. Now when we're talking about energy levels, we're going to want things in electron volts. So this really is the Planck's constant we're going to use the most. But I want you to be able to calculate with both. That's what we're after here. So, another thing. 1 nanometer is 10 to the negative 9th meters. Every time you see nanometer, you're going to do 10 to the negative 9th meters. So, 700 nanometers is 700 times 10 to the negative 9th meters. 550 is 550 times 10 to the negative 9th meters. 400 nanometers is 400 times 10 to the negative 9th meters. So, to find the frequency, we need things in meters. If we have the wavelength and we want the frequency, we're going to use this. So the frequency is the speed of light, 3 times 10 to the 8th meters per second, divided by 700 times 10 to the negative 9th meters. When you put this in your calculator, be sure to use the E button. It's the second comma button. That's going to do the times 10 to them. And you just have to write 3E8 or 700E negative 9. And then you don't have to do as much with parentheses. So when you do that, the frequency for this red light comes out to be 4.29 times 10 to the 14th hertz. When you do it for the yellow light, frequency of the yellow light, you do the same thing, 3 times 10 to the 8th, but this time you're dividing by 550 nanometers. You get 5.46 times 10 to the 14th hertz. And when you do it for the violet light, frequency of the violet light, you use 400 nanometers instead, and you get 7.5 times 10 to the 14th hertz. That's how you get frequency. To get the energy is equal to H times the frequency. This time, though, because we want energy in joules, we have to use the top one, joules seconds. So it's going to be the frequency. Sorry, yeah, it's going to be the Planck's constant 6.63 times 10 to the negative 34 joule seconds times 4.29 times 10 to the 14th hertz. Seconds and hertz, which are 1 over seconds, go away. And for the red light, our energy comes out to be 2.84 times 10 to the negative 19th joules. And again, that's really small, but that's because we're in joules and we're talking about a very little bit of energy per photon. When you do the energy for the yellow light, you take Planck's constant, multiply it by this frequency, and the yellow light comes out to be 3.62 times 10 to the negative 19th joules. And when you get the energy for the violet light, sorry, this should be a V, you're going to take the frequency of the violet light, multiply it by Planck's constant, and you're going to get 4.97 times 10 to the negative 19th joules. That's the energy of this light in joules. So the energy of each in electron volts, it's the same thing, but we're going to use a different H. We're going to use the H for electron volts. So 4.14 times 10 to the negative 15 electron volts per second. An electron volt is just another way to measure energy. It's much smaller. That's what we're after here. An electron volt is helpful, because we're talking really about electrons moving, we need to have an energy that's scaled down. That's what an electron volt does. So, Planck's constant in electron volts times the frequency of 4.29 times 10 to the 14th hertz. When we multiply that out for red light, we get 1.77 electron volts. It's a much nicer number to deal with. When we do it for the yellow light, we do 5.46 times 10 to the 14th times 4.14 times 10 to the negative 15, and we get 2.26 electron volts. And when we do it for the violet light, we use the frequency of the violet light times Planck's constant, and we get 3.11 electron volts. We are going to use electron volts more than anything else. So, the table to the right shows the electron levels for hydrogen. How much energy is lost when an electron falls from the n equals 6 state to the n equals 2 state. So we're going from here down to here, and what we're going to look at is the difference in energy. Okay? My difference in energy is going to be the energy in the n equals 2 state minus the energy in the n equals 6 state. We're falling down. Okay? So that change in energy is negative. We just want the difference between these two, right? So it's negative 3.4 minus negative falling 0.38. When we do that, our difference comes out to be 3.02 electron volts. So when it falls, we lose this energy. When it falls, we have a photon that's emitted. And this photon has an energy of 3.02 electron volts. And that's what our next question is after. What is the frequency of this photon? Well, this frequency is going to be energy over Planck's constant. Now my energy is in electron volts, so I need to use Planck's constant for electron volts. 4.14 times 10 to the negative 15th electron volt seconds. That gives me a frequency for this light of 7.29 times 10 to the 14th hertz. We're going to use the energy emitted to find our frequency. And then if we want the wavelength is going to be the speed of light c over the frequency. So the wavelength is going to be 3 times 10 to the 8th meters per second divided by our frequency of 7.29 times 10 to the 14th hertz. So when you do that, you get the wavelength to be 411 times 10 to the negative 9th meters, which also is 411 nanometers. All of those are acceptable as well. So, could an electron in hydrogen, one of these, ever emit a photon of wavelength 121 nanometers? So to do this, what we need is the energy of this photon. And that energy is hc over lambda. And we have to use this one because they're giving us a wavelength. So that energy is h in electron volts, 4.14 times 10 to the negative 15th electron volts, times 3 times 10 to the 8th meters per second, that's the speed of light, divided by our wavelength, 121 times 10 to the negative 9th meters. Don't forget to convert that 121 nanometers into meters. Now, when you do all that, the energy comes out to be 10.26 electron volts. If we wanted to, we could round that to 10.3 electron volts. And so if we look at 10.3 electron volts, that's going from the ground state to n equals 2. So if we wanted to kick out something with 10.3 electron volts, that corresponds exactly to this gap. So that's a big yes. It's possible. So, yes, it could happen. The electron would fall. It would fall from n equals 2 to n equals 1. I don't know what's happening with the ink. It's very strange. So, starting at the n equals 4 level, if we just stay there, there are 3 photons that could be emitted. So the first one, second one, and the third one. So we're going to go from n equals 4 to n equals 3, from n equals 4 to n equals 2, and from n equals 4 all the way down to n equals 1. And we're going to take the difference between the n equals 4 energy, 0.85, and all the energies below it. So the first one we have is 0.85 and 1.51. That's 0.66 electron volts. The next one we have is from 0.85 to 3.40. That difference is 2.55 electron volts. And then we have from 0.85 to 13.6. That's 12.75 electron volts. Now, for these differences, they're always going to be positive. But when an electron falls, it's going to kick out a photon, and when an electron moves up, it's going to absorb a photon. So, find the frequency of each. Didn't leave a lot of room there, and for that I apologize. So, to find the frequency of each, we'll find the frequency and the wavelength of each. The frequency is going to be E over Planck's constant, and then the wavelength, lambda, is going to be the speed of light over the frequency. I'll show the first calculation. So for the first one, that frequency is 4.1, did that backwards? That frequency is 0.66 electron volts divided by 4.14 times 10 to the negative 15th electron volt seconds. So for the first one, the frequency comes out to be 1.59 times 10 to the 14th hertz. And the wavelength for that is going to be 3 times 10 to the 8th meters per second divided by this frequency of 1.59 times 10 to the 14th hertz. The wavelength for that comes out to be 1886 times 10 to the negative 9th meters. So that's for the first one. I'll let you do the calculations for the other one, but for the second one, the frequency comes out to be 6.16 times 10 to the 14th hertz, and the wavelength comes out to be 4.87 times 10 to the negative 7th meters. And then the third one, the frequency comes out to be 3.08 times 10 to the 15th hertz, and the wavelength comes out to be 9.7 times 10 to the negative 8th meters. So, I know it's a lot of work, but you need to be used to making these calculations. I'm going to quiz you over whether or not you can convert between these things. It's important. So on that note, this is 1886 nanometers, this is 487 nanometers, and this is 97 nanometers. You need to be able to do that. Here's more practice. What's the energy of a photon of wavelength 487 nanometers? Since it's wavelength, we're going to use h times c over lambda. So that's going to be 4.14 times 10 to the negative 15th electron volts times seconds times 3 times 10 to the 8th meters per second divided by 487 nanometers, or 487 times 10 to the negative 9th meters. And it needs to be in meters because we need our units to line up. Put all that in and we get 2.55 electron volts. And yeah, that is a decimal spot, 2.55 electron volts. What will happen when this photon encounters an electron at the n equals 2 energy level? So what we would do to this is for the n equals 2 energy level, add to the energy there. So at the n equals 2 energy level, the energy of n equals 2 is negative 3.4 electron volts. When we take negative 3.4 electron volts and we add 2.55 electron volts, let me do that real quick. Negative 3.4 plus 2.55. We get negative 0.85 electron volts. When we look at the chart, it turns out that that's the n equals 4 level. So our electron goes from n equals 2 to n equals 4. It absorbs the electron and jumps up 2 levels. There you go. What is the energy of a photon with wavelength 500 nanometers? Same thing we did in part E. You had hc over lambda. So 4.14 times 10 to the negative 15th electron volts seconds times 3 times 10 to the 8th meters per second divided by 500 times 10 to the negative 9th meters. That gives me an energy, let me look here, it gives me an energy of 2.48 electron volts. So what happens when this photon encounters an electron at the n equals 2 energy level? We're going to do the same thing. So negative 3.4 electron volts. That's my n equals 2 energy. We're going to add to that the 2.48 electron volts. And when we do that, we see negative 0.92. And looking on there, that doesn't correspond to anything. So this photon is not absorbed and nothing happens. In order for a photon to be absorbed or emitted, it has to correspond exactly to the energy jump between energy levels. Otherwise,